Section 2.5 is on continuity. So we're going to talk about what makes a function continuous. The easiest thing to think about is a function is continuous if you can graph it without picking your pencil up. If I have to pick my pencil up to continue, then it is not continuous. So what are some things that would make it not continuous? A hole, or an asymptote, or a jump. Okay? So mathematically, I'm going to say a function is continuous at a number A if the limit as x approaches a of the function equals f of a. We've done a lot of problems where you're finding f of 2 or the limit as x approaches 2. So if a function is continuous at some number, some constant, then the limit has to equal the function value. Okay? So in order to do this, for every problem there's going to be 3 requirements. Okay, the first thing you're always going to find is f of a. So if f of a exists, the function has to be defined at the number a. Second thing is the limit must exist. Now, in order for the limit of the function to exist, that really is implying what? That the left limit equals the right limit. Okay? And then step 3 is if they both exist, now in order for the function to be continuous, the limit has to equal f of a, the function value. Okay, so those are your 3 rules that you're always going to show and write out for continuity at a number. Okay, if I look at this example, I already have the graph drawn. Example of the graph, is the function continuous? So just looking at this, it's not continuous. It has breaks in it, it has holes. So at 1, is the function continuous? No, because we have a what? We have open circle. Now in terms of the rules, I would say because f of 1 does not exist. So f of 1 is not defined, therefore it's not continuous. Okay, at 3. So f of 3 exists. F of 3 would be equal to -1. But the limit at 3 does not exist. So this would also be no, since the limit as x approaches 3 of my function does not exist. How come? Because the left limit would be equal to -1 and the right limit would be equal to 2. And then the last one, 4, would also be no. And now this is because if you look, if I go through the steps, f of 4, guys, is 2. The limit at 4 is 1, but those 2 are not the same. So no, because why? Because the limit as x approaches 4 of the function does not equal f of 4. So all 3, those are not continuous, but that's how I'm going to actually show it. Okay, so draw each situation. So I want to sketch a graph where f of a is defined, but the limit does not exist. There's different scenarios we could do for this. Quick one that I'm going to do is here a. So if I want a to be defined, I have a closed circle, and I would go in this direction, open circle this direction. So f of a is defined, but the limit doesn't exist because it breaks. Okay. Second one, draw an example where the limit exists, but the function isn't actually defined at a. So now I have a closed circle going in both directions. The limit would exist at a, but the function is not defined. And then the last one, I want both to exist. So there's f of a up there, and here let's say the limit would exist, but they're not equal. So there's an example of each scenario that is breaking continuity. All 3 of those are not continuous at a, and that's the reason why. Okay, next we can actually, we have names for the types of discontinuity. So if something's not continuous, okay, the first type is going to be called removable, which is also called point. Okay, all this means is I have an open circle. So if I want to draw a quick sketch of this, there's a removable discontinuity. If I just filled that circle in, I'd be okay. I just have one point where it's not continuous. I have a hole in the graph, okay? The second type of discontinuity is called infinite, or sometimes referred to as essential, okay? All this is it means I have an asymptote, okay? So here's my example. If I have an asymptote and the graph looks like that on both sides, it's not continuous. I jump over the asymptote. So it wouldn't be continuous at the asymptote. And the third type is called jump, where the graph literally breaks and jumps from one y value to the next. So all three of these cases are discontinuity at some value a, and that's what they're called. I can be continuous from the right and left. So if I were continuous from the right, that would just mean the limit as x approaches a from the right of my function is going to equal f of a. I don't have to worry about checking from the left. I would just do those two. And from the left would be the same thing. From the left of f of x would equal f of a. Okay. Next slide's a whole bunch of information. Okay, so to be continuous on an interval, if continuous at every number in the interval. If f is defined only on one side, then we understand continuity to only mean that one side. Okay, here's the important part. A polynomial, x squared, x cubed, x to the fourth is continuous everywhere. Negative infinity to infinity. Okay, a rational function, 1 over x minus 3, is continuous where it's defined. So obviously it's not continuous where it's going to have an asymptote. And then all of our functions, polynomials, all of these are continuous for every number in their domain. Okay. Next rule is just talking about the composition of functions. So if I want to take the limit of f of g of x, what can I actually do first? I can just find the limit of g, and then afterwards I can find f of that value. Okay, so I have an example to show this. So here's an example. Limit as x goes to 1, arc sine of that function. So what can we actually do? We can first find the limit as x goes to 1 of the inside function. Then I can take the arc sine of that afterwards. Okay, so you could pause this now and you could find this limit algebraically using our techniques that we've used. So what are we going to do? I cannot just plug 1 in because I'd get undefined. So here's a problem where I'm going to rationalize the numerator, root x, which would become the limit as x goes to 1 of what? Of 1 minus x over 1 minus x times 1 plus root x. These are going to cancel. So I'm going to be left with the limit as x goes to 1 of 1 over 1 plus root x. Now I can plug my 1 in, and I'd have 1 over 1 plus root 1, which is 1/2. Now, to finish the problem, I would do arc sine of that value. And we know that that just means when does sine equal 1/2? So my answer is pi over 6 using my unit circle. Okay. Next is a theorem called the intermediate value theorem. It's a little blurry, sorry. So in your notes, this is what it's defined as. Given a continuous function, that's why it's thrown in here, on some interval, the function hits every y value between the starting and ending values. Here's another explanation. So I have this continuous function, kind of looks like an x cubed. Okay, so if I'm saying I'm starting at A and I'm ending at B, okay, it's going to take on every single y value between f of A and f of B. Okay, so say f of A is 1 and say f of B is 5. The function is going to hit every single y value between 1 and 5. Kind of obvious. Why? Because the function is continuous. So that's the key. Okay, the most common problem that you're going to see with this is proving that there is a root or a 0. So look at the next problem. Should be show that there's a root of this function between 1 and 2. Okay, so the idea here is I'm starting with 1, I'm ending with 2 for my x values, and it must hit every single y value in between. So if I let f of x be the function, x squared plus 3x minus 2. Okay, and I find f of 1. So go ahead, if you plug 1 in there, you're going to get negative 1. And you find f of 2, you're going to get 12. So now what does the intermediate value theorem says? It says that if that function's continuous, it's going to hit every single y value in between negative 1 and 12, which means it must equal 0. So now, how am I going to write this? Okay, I'm going to say since f of x is continuous, okay, on that interval, so continuous on what? 1 to 2, and what? F of 1, which equaled negative 1, is less than 0, which is less than f of 2, which equals 12, then what? Then there must be some value, so there must be a value c, we'll call it, okay, in 1, 2, such that f of c equals 0, and why? By the intermediate value theorem, IVT. Okay, all that's saying is there's got to be a root between 1 and 2. How come? Because 0 is in between negative 1 and 12. So how are you going to do these problems? If you're trying to prove there's a root, you just need to show that the two y values go from negative to positive or positive to negative. Right, now there's just some practice problems for continuity. So the first one is the function continuous at 2? So go way back to the beginning. In order to be continuous, what do you have to show? First thing, you have to find f of 2. Okay, so f of 2, I would use the bottom part, which is 2 times 2 minus 1, which is 3. Next, I'd have to find the limit. In order to find the limit, I'd find the limit from the left and from the right. Okay, from the left, I'd be using the top part of the piecewise function. Plug 2 in, I get 3. From the right, I'd be using the bottom part, and I have 4 minus 1, which is 3. So therefore, the limit as x approaches 2 of my function is 3. Okay, and then since f of 2 equals the limit as x approaches 2 of f of x, which equals 3, f of x is continuous at 2. What did you really just prove? You just basically proved that this function comes together at 2. The left side and the right side meet at the point 2, and it's a filled in point. Therefore, it's continuous. You could graph it to see, you don't have to, but that's really what we just did. Next one's really similar. Is the function continuous at 2? So you would do the exact same thing. You would first find f of 2. F of 2 is going to be, what, 2 squared, which is 4. Next, the limit as x approaches 2 from the left. From the left, I'd be using x plus 1, plug 2 in, which I get 3. I can stop. Actually, no, I should find, the limit as x approaches 2 from the right. From the right would be the 2x minus 1, and I also get 3. Therefore, the limit as x approaches 2 of my function is 3. Now, I have the function exists and the limit exists, but they are not the same, so therefore it's not continuous. So since f of 2 doesn't equal the limit as x approaches 2 it's not continuous at 2. Not continuous at x equals 2. Okay. Third one. A little different. For what value of a, now you're trying to find the a value that would make this function continuous. So I still am going to do the same thing. Find f of 4. So what's f of 4? I'd plug it into the bottom one. 4 squared minus 4. 16 minus 4 is 12. Then I would do my limits. Limit, as x approaches 4 from the left, would be what? Ax plus 5. So it would be 4a plus 5. Okay. And the limit as x approaches 4 from the right would be the x squared minus 4 minus x. Plug 4 in, and I get 12. So therefore, in order to be continuous, what must be true? 4a plus 5 would have to equal 12. Now you could solve for a, subtract 5, divide by 4, and I get a to be 7/4. Okay, so to be continuous at 4, a would have to be 7/4 in order to make the limit equal the function value. Okay, last one. Where does this function have an essential discontinuity and a removable discontinuity? Okay, so remember, essential discontinuity really just means asymptote. So how do you find the asymptote of this function? Well, you could just factor. Okay, so if I factor, we get what, guys? X minus 5 and plus 4. Numerator, I'm going to factor as, let's see, plus 3 and minus 5. Okay, so now looking and remembering from last year, what's happening? It has x minus 5 in common. So that is actually where there's going to be a hole in the graph, which would be my removable. So part B would be at x equals 5. Okay, part A would just be the asymptote, which would be at -4. So the asymptote is my essential. So essential is your asymptote. Your removable is your hole. What if you want to find the y value of the hole? If you remember, once I cancel these, the function just becomes 2x plus 3 over x plus 4. So now to find the y value, I can plug the 5 into that. So I would get what? 13/9. So the y value would be 13/9. Okay, so that would actually be the point for my removable discontinuity.